Hey there, folks. We are back, and I want to talk to you about some new stuff. We're going to skip around a bit and move into what are called relations. And you guys remember that term relations, I would think. You know, back when you were taking algebra and you started to talk about functions, before you talked about functions, you typically get there pretty quick, but you spent just a few minutes probably talking about relations. And relations is just, a function is simply a relation that satisfies certain criteria. So I'm going to start very general. Let's talk about relations. And before I do that, I actually want to define something I think you probably have seen. Let me get my mouse out of the way, sorry. You've probably heard of these things before, but I just want to make sure the Cartesian product of sets A and B denoted A cross B. Okay, and that's another symbol that's overused. The X or the cross. We use it initially for multiplication when we're in grade school, and then you take linear algebra, and it means a certain thing with crossing two vectors, and then the cross product, right, of two vectors, and then now it's something else. But the context helps a little bit. Because we're talking about sets, there's no way this is a cross product. It's what we call a Cartesian product, named after René Descartes, or René Descartes. So okay, here we go. This is what we mean by this. The Cartesian product of sets, denoted like that, is the set of ordered pairs of form A cross B, where A is an element of the set A and little b is an element of the set B. Okay? So, for example, if I'm talking about the cross product between, here's a set with A, B, and C in it, crossed with a set that has a square, a triangle, and a circle in it, then what's in that cross product? Well, okay, I got A square, right? A triangle, a circle, and then B square, B triangle, B circle, that's a very small circle, sorry, and then C square, C triangle, and C circle. Okay, so that's what we're talking about when we talk about the Cartesian product. The notion of a relation is just a subset of that. So a relation between these two sets would be some collection of the elements in that Cartesian product. And so there's several, right? In a case like that, you ask the question, well, how many subsets can you make of that Cartesian product? Well, each thing in there, there's 9 things in there. 3 times 3 gave us 9 things. And then each one of them could be either in the subset or out of the subset. So you got, for each one, 2 choices. So you end up with 2 to the 9 different possible relations or different subsets. Or relations between those two sets. Okay, so let's go ahead and define that formally. a relation from set A to set, I meant to call it something, let's call it relation R, excuse me. Relation R from a set A to set B is a subset of A cross B. All right. And there's a little bit of notation that goes with that. If AB is in the relation R, then we will sometimes write A, R, B. And I'll give you some examples here in just a minute that kind of make it clear why we would do something crazy like that. I'm going to go ahead and keep defining things since we've got all these R's and A's and B's here. The domain of the relation, probably out of room, is the set of things in A that are in the relation. So set of A in the set A, okay, such that AB is in the relation for some B. I guess that's probably the way to do it. Is the set, and I'll get that of out of there. Okay. So it's everything in the set A, okay, that has an ordered pair that goes with it. Okay. The range, you've seen these words before, of R is the set B in set B such that AB is in, didn't mean to put 2. I'm so used to using real numbers, I almost, such that AB is in the relation for some A in the set A. Okay? So relation, the notation, what we mean by the domain, and what we mean by the range. Okay? It's important to kind of point out that the relation really is more than just having the same sets that you start with. This gives us a Cartesian product, but the relation is some subset of this. Okay? So, for example, okay, if this is set, okay, I'll just do it. If A is ABC and B is square, triangle, and circle, then this set, and so just take a few things out of this. A square, a circle, B square, is a relation R on, not on, sorry, from A to B. Okay? The domain is A and B. And the range is square and circle. Okay, does that make sense? Kind of what we're talking about there. But the thing I was kind of harping on is if we can talk about relations that are the same, but it has to be more than just having the same two things, the same domain and range. You've got to have exactly the same ordered pairs in the relation. Okay, so just because A and B are used again doesn't mean we'll get the same relation. We've got to get exactly these ordered pairs. Okay, all right. So let me expand upon this slightly, because I want to talk about relations on a single set. Okay. Relation R from A to A, which there's no reason that we can't have the same set for the first set and the second set. This is said to be on A. So we'll talk about a relation R on A. And we actually, when we start to kind of list some relations here in a moment, I think you'll realize that we deal with relations quite a bit, actually. Let's talk about types. Types is probably not, yeah, I guess it is. Really classifications, types of relations, or perhaps maybe not types as much as it is properties. There we go. I'm feeling better about that. Properties of relations, okay? We say that R is symmetric. Oh, that's not where I meant to start. That's okay. I'm going to start here. If having A related to B, and I need to properties of relations on a set, because the A and the B here have to be in the same set for this to work. If having this A related to B implies that B is also related to A. Okay? An example of a symmetric relation equals on anything, natural numbers. Okay? You take any kind of natural number same element here, that implies, maybe that's not the best example, equals, oh, I know, well, no, that works. It implies to switch the sides, the same thing, but that's really not probably the best trying to think of a good example of symmetry. Think of a great example that's not. Would be less than, right? On, say, natural numbers. A less than B does not imply that B is less than A, right? Okay. Yeah, equals is a good one. I'm trying to think of other things we could do with numbers where if it goes one way, then it goes the other way. This will that wouldn't work either. Let me think of that. If I think of a good one on the way back out, I'll say something about it. Okay, here's symmetric. Here's actually the one I meant to list first. R is reflexive. I'll turn the sound down. If what we mean by that is you always have an element related to itself. Okay, so again, here's a great example. Equals on, say, the natural numbers, because every natural number A is equal to itself. Okay. Man, I think some good examples, but I don't want to have to define something just to show symmetric. Okay. And again, I can go, here's an example of not less than on natural numbers. Right? Does not happen. Okay? This was a not example. Not. Right. We say that R is transitive if and only if having A related to B and B related to C then implies that A must be related to C. Okay? So for an example on this one, now here's a case where I actually can kind of throw in less than on the natural numbers. If we have something that's less than B and we have B which is less than C, then that does imply that A is less than C. Okay? Divides is another one. If A divides B and B divides C, then A divides C, for example. Okay? Trying to think of some good non-transitive examples. You can think about that one too. Okay. And then this is kind of weird because with rational we do something like irrational. We say, well, it's not rational. I can't exactly say this with this next one, which is R is anti-symmetric. This doesn't mean that it's not symmetric. Okay, it means something completely different. It means that if, and this will look familiar to you, if we have A related to B and B related to A, then that implies that A and B are the same element. That's the only way that can happen. Okay. So for an example, less than or equal to, right? Because we know that if A is less than or equal to B and B is less than or equal to A, then that forces us to have A and B be the same thing. Okay? So, really the homework is, and I'm not going to do, I've shown you a few examples, but really what I want you to do is go through those homework problems and start to play with these ideas. The homework kind of leads you into many of the thoughts we have about these concepts, and then we'll eventually kind of lead into some proofs. But many of the homework problems actually introduce concepts kind of similar to this. So I want to get you going, but then let you take it from there. So in 5.1, do these problems. 5 through 7, and then 9 through 10, 15, and then do problem 17. So that will give us a few problems to work on. We've still got some stuff out of 3.4 to work on. Remember that Tuesday in class I will take up your homework from 3.1. Okay? So, all right, I'm going to kick it in the head right there. And I will see you in class on Tuesday.